We're continuing our discussion of the problem on using a fusion reactor. In part A, we have calculated the intensity as a function of energy that enters the spectral emittance calculation. And in part B, we found the maximum intensity energy, that's 2.821 kT. Now in part C, if the device is designed for 1000 Kelvin, then how much power is supplied by the motor and what's the current I? Hint, integrate the spectral emittance around the black body. Okay, now we're operating at a temperature of 1000 Kelvin. So we are at a temperature of 1000 Kelvin. The maximum intensity energy is 2.821 kT. Now we can convert this to joules. We know that the kT value at room temperature is 1/40 electron volts. And room temperature is roughly 300 Kelvin. So this can be written as 2.821 1/40 electron volts, convert to joules, 1.6 10 to minus 19 coulombs. But here we're operating at 1000 Kelvin instead of 300 Kelvin. So this will be multiplied by 1000 over 300 to convert this kT value to the kT at room temperature to the kT value at 1000 Kelvin. So this will give us an E0 value of 3.76 times 10 to minus 20 joules. Okay, so now we're told that the photodetectors that are at the surface of the inner sphere will capture photons that have a certain energy range. So with energies E0 plus or minus delta E. And this delta E was defined to be 1% of the energy. So E0 plus or minus 0.01 E0. Now, if you look at the intensity versus wavelength plot here, this has a tail. And when we are close to the peak point, we see that the intensity is approximately a constant. So if we take this window E0 plus delta E, E0 minus delta E, so this is E0 plus delta E, and this is E0 minus delta E here, we can calculate the spectral emittance in this energy range. Okay, so we note that the intensity, maximum intensity, which is at an energy of E0, is approximately a constant. In this range. So the total power that will be detected here is the intensity at energy E0 multiplied by 2 delta E to find the spectral emittance in this energy range. That's the total intensity detected. And if you multiply it by the surface area, because intensity is power per perpendicular area, we will get the total power. So this is total detected intensity multiplied by the area, the surface area. And this is equal to 2.843 pi kT cube divided by h cube c square, that's the maximum intensity, multiplied by 0.02 E0 multiplied by the surface area 4 pi r squared. So we have the maximum intensity here plugged in 2 delta E, that's this window, and define 2 delta E at times the maximum intensity is this window, multiplied by the area 4 pi r squared. So we can calculate this power, detected power, 2.843 pi kT cube 1 over 40 electron volts times 1.6 10 to minus 19 to convert to joules times temperature is 1000 instead of 300, 1000 divided by 300 cube multiplied by 0.02 E0, 0.02 times 3.76 10 to minus 20 joules times 4 pi r square, 1.23 meters square, divided by h cube, 6.63 times 10 to minus 34 cube, c squared is 9 times 10 to 16. So let's check these numbers here. The radius of the black body is 1.23 meters, and we have the maximum intensity given by this expression. Temperature is 1000 Kelvin, and we have already calculated E0 in joules. Okay, so if we perform this calculation, we find the total power to be 11.5 kilowatts. Okay, so in part C of this problem, if the device is designed for 1000 Kelvin, then how much power is supplied by the motor? That's what I have found. And what's the current I? Now, we are told that the device has a resistance of 1 kilo ohms, and the power delivered is going to be consumed by this resistor. So it is I square R is the power. So we can calculate the current delivered to be square root power divided by the resistance, and that is 11,500 watts divided by the resistance, which is 1 kilo ohms, 1000 ohms. So this gives us finally a current value of 3.4 amperes. All right. Let's move on to part D. If the device is designed for 5000 Kelvin, then how much power is supplied and what's the current? So we're changing from 1000 Kelvin to 5000 Kelvin. Now, if we look at the E0, it is linearly proportional to temperature. So we can say that the E0 value will be increasing linearly with temperature. So the new E0 value at a temperature of 5000 Kelvin will be the one at 3000 Kelvin multiplied by 5. 5 times 3.76, 10 to minus 20. This gives us 1.88 times 10 to minus 19 joules. On the other hand, the power varies as t to the fourth power. So we can see here we have kT cube, and then we have from E0 another factor of kT. So the power varies as t to the fourth power. So we can see that the power that we have calculated will be 5 to the fourth power times 11.5 kilowatts. That will be the new power. So this will give us a power of 7.2 megawatts. The current, on the other hand, is proportional to square root of power, which is proportional to t squared. So we can say that the new current value will be the old current value multiplied by 25, 5 squared. So this will give us an operating current 85 amperes. Okay. So in this part of the problem, having calculated the intensity as a function of energy for the spectral emittance calculation and having found the maximum intensity energy by taking the derivative with respect to energy, setting it equal to 0, we can now look at what happens at 1000 Kelvin to this maximum intensity energy. It's 3.76 10 to minus 20 joules. The photodetectors are detecting the power emitted by this black body. So they will capture photons with an energy range E0 to E0 plus or minus 0.01 E0. And the power that will be detected is the spectral emittance for this window multiplied by the surface area of the sphere, which is 4 pi r squared. And this power is basically used to supply is basically supplied by the motor. And what's the current I? And we can calculate the power is equal to I square R, given that the resistance is 1000 Kelvin. So it was here an EMF across a motor of resistance 1 kilo ohms. So we have this power appearing on a motor with resistance R. So we can calculate the current that flows 3.4 amps from P is equal to I square R. And if we change the temperature, E0 will be increasing linearly with temperature. Power will be increasing kT cube coming from this maximum intensity and kT factor coming from E0 here as t to the fourth power. And the current will be scaling as t squared because it's square root P over R. So we can calculate the new values of maximum energy, maximum intensity energy, the power delivered, and the current that flows.